Test. Welcome back to the stream. Today a little bit earlier, I guess, than usual. Today I want to manage to stop streaming before Zoding finishes streaming, so we can finally host Zoding for a change. So that's the plan for today, basically. That's the main objective I have for today. It doesn't matter how far we get. It's important that we are able to host Zoding. As far as I know, he goes live at 6 p.m., which is maybe a little bit early to end right at that time, but a bit later then. Does this look like water to you? I feel sorry for the water supply you have. JP, I started a podcast like 3 years ago, and I made one episode and never another one. This had nothing to do with the Thugroad thing. I believe if you type in Live Overflow podcast, that's the first result basically that comes up, that podcast that I started. So about your question, if I've ever considered it, that answers it. Yes, I've considered this. Yes, I've even started. I have not continued. Yeah, and the song is The End is Near. No, not Jingle Punks. No. That must be then a remix or something. The original what's the name? Performer is Gunnar Olsen. The End is Near Gunnar Olsen. Do you know any good reading materials about anger? I tried reading through the docs and still feels like I can't do shit with it. Yep, that's right there is the problem, the internal problem that we always have with documentation and using tools. All I can say to you that these are advanced professional tools that are not made for basic end users. The only advice I can give you is look for examples that other people have done. And Anger has actually quite a nice collection of examples, I believe even in the official repository. So the documentation is more meant as kind of a reference if you kind of get stuck with something, but I would rather encourage you to kind of like, if you have an idea how to apply it, then look for an example that seems to be similar to what you do and then start adapting that. I think that's the best thing to do. And maybe I would also, maybe you are lucky, also find some talks or workshop recordings from Anger on like YouTube or other course material like slides. That's the other, I'm not sure about that, I've never looked that up, but that is the other general tip that I would give. Just look for like slides or talks about it. Use jQuery. What's that about? All right. Anything else? I think I have nothing else to. Did anything happen since yesterday? No, I don't think so. I think nothing happened. Yeah. Give me 1 second here. I forgot to set up chat on this computer here. Otherwise, how is everybody doing today? How is the heat wherever you are living? What's the weather like in Germany? It's really nice, warm and sunny outside. So it's, yeah. I wouldn't say it's like crazy hot, I believe. It's like 30 maybe, 33 or something, tops. Let me see. Where I'm at least. I don't know what the rest of Germany looks like. Yeah, it's 31 degrees right now. 34 degrees in Hong Kong. Yeah, the humidity. Yeah, that is killing. 10 a.m. in Mexico. Wow. All over the place today. CMAX Media even from Australia, like from the other side of the world. That's insane. Sweden has like 25 degrees. Is that warm for Sweden? I have no clue. Right. Let me see. I tried to get everything in order. I didn't really prepare the stream. So I still like everything left over from like yesterday. So yesterday we finished the so the RAM module was finished kinda, and then we finished then we made the instruction register, which we also tested, so that seems to work. So currently our state is actually pretty good, I believe. Let me get that camera here on. Why are you dark? You shouldn't. That's a little bit concerning. Why are you showing a dark screen? Well, what happened there? Exposure and brightness are messed up? No, I don't believe so. I didn't change anything. The ISO is at 200. We have a 60th exposure. Should be all good. Okay, so now this screen here is working. I did unplug it from the USB previously, so I feel like... Oh, wait. Oh. My capture thing on my PC has crashed. That's the reason why. It's weird though that it still showed here like a black screen on the camera itself, but it's like this weird USB connection, so maybe it was like, I don't know. Great, that completely broke now also my settings. Let's see if we can go back here. Oh my gosh, I don't know what's going on. So the video view of this camera seems to be broken right now. It's weird. I mean, we can work with the regular. It's just black. Like the video view is just black. And the regular photo view works. It has a wrong aspect ratio though. Oh wait, now it crashed again. Okay, weird. Oh my gosh. Okay, everything is annoying right now. Okay, whatever. We will make do with this view. It doesn't have the perfect aspect ratio, so we have the black bars on the side, but it will be good enough, I think. Let's also get yeah, good enough. Let's see. Can't change the this is really irritating right now. Okay, well, whatever. Doesn't look as nice today. Yeah, it was working. So this camera has like a photo mode and a video mode, and on the photo mode, like it works right now. You see a screen, but it's not as great as if it's on the video mode. Or at least I did all my settings on the video mode, so now it's on the photo mode. Now some color settings and things like that are different, and also, yeah, it's just different. I don't know. Oh, by the way, thanks Fermented Rye for the Twitch Prime sub while I was offline. Okay, one last try. I kind of want to try again here. Let's turn this off. Switch to camera mode. And let's turn it back on. Oh, yeah, we are back. Okay, cool. That fixed it. Now we have the nice of... I mean, it's barely different, but whatever. Okay, so here. Oh, it's so noisy. Why is it so noisy? That's weird. What happened since yesterday? Huh. Oh, thanks for the Twitch Prime sub, Alevsk. Thank you. And sorry for this scuffed start. I think I fixed it. I think we're okay. Somehow all my settings got wrecked. Anyway, okay, so we are back. So basically, we have finished the instruction register yesterday. The instructions are also 8-bit, and the instructions will be in the initial settings. How Ben Eater has it designed is designed in that way that the first 4-bit kind of like decide the instruction, and then if there's an instruction that references memory, for example a move instruction that moves stuff around in memory in RAM, then the other 4 bits are the address. And as you know, our RAM only has 16 bytes, and so the 16 bytes are addressed by 4-bit addresses. So you can also see the other, so up here these LEDs indicate like what address it's currently used in the RAM, and so yeah, so that's why they are both like 4 yellow LEDs. Yeah, and otherwise here's the RAM module. If you haven't seen it yet, looks pretty nice. And that works as well. It's pretty large because it includes, so this is only the RAM here, and up here and down here are just circuits that allow us by hand to enter values into the RAM by hand, because this is how we can write programs into the memory as well. We write all the single bytes for the instructions into RAM like that. Yeah. And over here, this is the stuff that we originally did. Those are the 2 A and B registers, and in the middle we have the ALU. So it's taking on shape. It starts to look really, really nice, don't you think? It starts to really take shape. There are a couple of modules still missing though. We kind of estimate that we are like, yeah, halfway, maybe a little bit over halfway there or so. I could never understand how the software and hardware actually interact. The series help you. Awesome, yeah. I think that's exactly why Ben Eater also made that series, because it gives you really a better sense and into understanding of yeah, of how computers work. You should create output modules, but just with the 8 LED and buffer. I'm not quite sure what you mean, but we will reach the output register that Ben Eater is building with the 7-segment display soon. The cables remind me of Factoria assembly lines. Looks awesome. Thanks. Yeah, it does. I spent quite some time on trying to make it look neat. And I think I also learned a lot. So this is the first module we built, and I feel this looks a lot more crooked and like not as nice as this build, which came a lot later. I think I also practiced here a little bit. You should also add LED on the bus. Yeah, for sure. I mean, this is the bus, and there are LEDs right now, so there are already LEDs on the bus, but obviously it's not the finalized bus. The bus will obviously be way different. But yeah, one step at a time. Let's figure out what the next video is that we have to watch in the series. Oh, we have some more basic videos now. Oh, wow, okay. So the next video in the series, I'm going to show you. So the next video, I remove my face really quick so you can see the title of the video. So the next video in the series is the introduction of the JK flip-flop. It's another variation of flip-flops. And if you look into the playlist, what's coming up, we watch now an introduction to the JK flip-flop, and then we have a JK flip-flop racing, which I don't know what that means. Maybe it's like trying to do the flip-flop so fast that it starts glitching, maybe? I don't know. Then we introduced the master and slave JK flip-flop, which is also, I also remember this kind of stuff from school. I don't remember the details, so I'm kind of looking forward to get a refresher of all that. And then we used that to implement a binary counter. And that will later become our program counter that is, you know, always incrementing to the next instruction. And then we finally built this. So it seems like today will be a more theoretic stream. We keep watching YouTube videos and talk about it. I don't know. So yeah, let's put on headphones. Are you guys ready? Ready to watch some YouTube videos? All right, so let's hit in.
Which I've talked about in a previous video.
What did I just do?
And I'd encourage going back and looking at that video if you're unfamiliar with it. But basically, the last...
Yeah, do you remember the SR latch? I think the SR latch is one of these things that are really like mind-blowing to think about. They are kind of like the... like they were that mind-blowing puzzle piece that I needed to kind of understand how like a computer, like this on the lowest level kind of works, because we all learn about these logic gates, these NAND gates, AND gates, OR gates, but they are, I talked about it in the charity stream already, but sorry if I repeat myself, but we have these gates, right? There are two NOR gates, for example, on that screen right now, where inputs are coming in, and then it's having whatever a NOR gate does, it has an output. But that seems so static, right? You put something in the input and something comes out of the output. How can that build anything that executes something, right? It's just you put something in the input and something comes out. Whereas the clock, like how would that be used to like execute something? How can that change over time and do different things according to the instructions? And I don't know, it seems so weird to think how the static thing becomes something so dynamic. And the crucial idea is that you start connecting the outputs back into the input, and that's what you see in this SR latch. It's breaking that mindset of it's just like inputs coming in and outputs. You break that because now you take the output and connect it back to inputs, and suddenly weird interesting behavior emerges. And that weird interesting behavior can be, for example, made into what we are calling an SR latch, which is basically like flip-flopping between set and reset, called like between Q and not Q outputs, whatever. It's yeah, and then based on that you can build a bit more complicated up until you get like the D flip-flop, and now we go even a bit further. Now we introduce the JK flip-flop, which is another kind of variation or improvement or advancement or modification of this idea of, yeah, we will see. I don't know. I love that.
Latch has two inputs, R for reset and then S for set. And when the reset goes high, then the output Q goes off, is reset. And then when the set pin goes high, then the output Q goes on. And then there's also an inverted Q, which is always the opposite of Q. Except for one case where if both reset and set inputs are high, then both of these go off. And that's generally considered an invalid setting, because you shouldn't be both setting it and resetting it at the same time. And in fact, if I then release both of these, it's kind of arbitrary which one comes on, because whichever one of these I'm releasing first kind of wins. But generally, yeah, the latch is going to latch in one of these two states. So in this video, what I want to do is talk about some modifications to this simple SR latch circuit. So the first thing I want to look at is the SR latch with an enable. So this is the basic SR latch that we just saw, but now we've got on both of the inputs, we have these AND gates that are connected to an enable signal. And basically what that does is if this enable signal is high, if it's a 1, then these AND gates pass through whatever the other input is. So if this is a 1 and reset is 1, then it passes through a 1. If this is a 1 and reset's a 0, it passes through a 0. If the enable is 0, then the output is always going to be 0. And so the latch, if enable is 0, the latch always stays latched in its last state. And so this just gives us a way to enable the latch, in which case it's going to pay attention to its two inputs, or disable it, in which case it just stays latched regardless of what happens to these inputs. So it's just a slight modification of the basic SR latch. We could take this a step further and turn this into a flip-flop. And the difference between the SR latch and the SR flip-flop is, and in general the difference between a latch and a flip-flop is that a latch, the outputs will change whenever the inputs change. With a flip-flop, the outputs are only going to change when there's a clock pulse. And so a flip-flop's always going to have some sort of clock input, and in the diagram for it, the clock is indicated by this little triangle signal here. And so then whenever the clock pulse comes in, or specifically when the clock transitions from low to high in this case, then the outputs will change, and only at that transition point will the outputs change based on whatever the inputs are at that point. The rest of the time it doesn't matter what's going on with the inputs. And so the way that works is we have this clock pulse coming in, and it's when it transitions from low to high, when this voltage changes here, you're going to get some current flowing through this capacitor as the capacitor charges. And so over here, you're going to see the voltage go up as soon as this transition takes place. But then once the capacitor charges, that voltage will drop, current will stop flowing once the capacitor is fully charged. And so this clock pulse, no matter how long this clock pulse is going to essentially show up over here on the inputs to these AND gates as this really quick pulse just at the point where that rising edge happens. And so that very quick pulse is used to essentially enable, if we think of what we saw before, the SR latch with the enable, it is essentially what's happening over here. And so that SR latch with enable is only enabled.
Was that Bing in the video, or was it my phone? Did he record where he got a text message?
And so that SR latch enable is essentially what's happening over here.
Oh, he must have been so annoyed and didn't want to redo it.
And so that SR latch with enable is only enabled just at that moment where the clock rising edge happens. And so that has the effect of it working like an SR flip-flop. So when the clock rising edge happens, then it looks at the R and S just at that moment where the clock rising edge is. And if reset is enabled and set is not, then it resets. So the output goes to 0 and the complement of the output goes to 1. If the clock rising edge happens and at that moment the set input is active and the reset is not active, then the output Q turns on and the complement of Q goes off. And then if there's a clock rising edge and both the reset and set inputs are 0, then it just stays in the last state. It stays latched like it normally would. And in any other case, no matter if the clock is not, if there's not a rising edge of the clock, if the clock is doing anything else, then it doesn't matter what the set and reset is doing. The flip-flop stays in its last state. Now there's one interesting case here, which is where if you have a clock rising edge and reset and set are both active, remember this is that invalid state. So if reset and set are both active, we saw before with just the SR latch, if both inputs are active, you see both the Q and the Q complement go off. And so you might expect that, right? Q and Q complement go off. But the reality is that when we release both of these, the latch does settle down in some state. And that's actually going to happen here too. One of these two inputs is going to be slightly ahead of the others, and the SR flip-flop is going to settle down into some state. So we really aren't actually going to have this output case where both Q and Q invert are both zeros. I mean, that's invalid, right? Because you would assume that the inverse of Q would be the inverse of Q. You would not expect it to be the same thing. And in fact, that's true. And the problem is with this situation where you have both a set and a reset when you have a clock pulse, it will settle down into some state, but we don't know what it is. So really, these are both kind of unknown what will happen. So this is again, kind of an invalid situation where we don't really know what's going to happen here because it just depends which of these is a few nanoseconds faster. You know, it's unpredictable. But there is something we can do to make that a little bit more predictable, and that is the JK flip-flop. And so the JK flip-flop is very similar to the SR flip-flop, except that it has this feedback coming from the outputs. And so it has these 3 input AND gates over here, and it's looking at the current state of the output Q and Q inverse in determining what's going to happen on the input. And as far as I know, you know, JK is just kind of an arbitrary set of letters. It doesn't mean anything.
It's a just kidding flip-flop.
But I guess this is different enough from an SR flip-flop that they gave it a different name. But anyway, if we walk through what's going to happen here, you'll see it's very similar. So if J and K are both 0, then it doesn't matter what else is going on. The output of these AND gates are both 0. And so we have this same situation where, you know, even if we get a clock pulse, we're going to stay in the last state. But now let's imagine a case where the latch is currently set. So Q is 1, inverse of Q would be 0, and we want to reset it. So if Q is 1, then this is going to be 1. And if we want to reset it, then we're going to set K to 1. So this input will be 1 because, you know, the current output is 1. It's currently set. K will be 1 if we want to reset it. And then when we get our clock pulse, this AND gate will turn on, and this will be our reset signal. And that'll reset the latch and turn Q off. And then, of course, inverse Q on. And so that's this scenario here where J is 0, K is 1 to reset it, and then we get our clock pulse, and so you see Q goes low. We reset the latch. But what if the latch was already reset? So if the latch was already reset, then Q is already low, and we set K high, and basically this stays off. And of course J is also low, so this stays off. So we have both zeros, and so we stay in the last state. But that's okay, right? Because if we wanted to reset it, we're setting K high to reset it, and it was already reset, then it's fine to leave it in the last state, right? It was already reset, and we want to reset it, leave it in the last state. So that works fine. And same thing in the opposite case. So if it's currently reset, so Q is low and inverse Q is high, then that means this is high. And so if it's currently reset and we want to set it with the J, then both of these inputs will be high. And then when we get our clock pulse, this input will go high, or this output of the AND gate will go high, and we'll reset the latch. And so you can see in these cases it works basically the same way as the SR flip-flop. It's just that we have the inputs are called J and K instead of S and R. So where the JK flip-flop gets interesting is if both J and K are 1, because in that case, because you've got this feedback here, J and K are both 1, but these other two signals, these feedback, are not going to be both 1, right? Because either Q or not Q is going to be high at any point in time. You're not going to have both of them high, right? So if Q is high, then this lower AND gate will be active, and the top one will be off, right? You know, even if J and K are both 1. If inverse of Q is active, then the top AND gate would be on, and the bottom one would be off. So what this does is it means if the latch is currently set, then effectively what's going to happen is this lower AND gate is going to come on and the latch will reset at the next clock pulse. Whereas if the latch is currently reset, then the top AND gate would be on and the latch would then set at the next clock pulse. I mean, assuming J and K are both 1. And so that gives you this very interesting state where instead of getting some invalid or unpredictable output, you get this very predictable output, which is it'll just toggle. So if Q was 0, it'll switch to 1. If Q was 1, it'll switch to 0. And as you'll see, that's a very interesting property.
Very interesting.
In a previous video...
Okay, did everybody get that? The JK flip-flop is an extension of the SR flip-flop where we are feeding back the output of the SR flip-flop again into the input and AND it. And basically it just gives us this additional property of that toggle, which yeah. It makes it a little bit more complex again, but it gives us a new interesting property that we might be able to use, and as we know, it will lead to the program counter, as the futurist already mentioned. Yeah. Now what's JK flip-flop racing?
We looked at the JK flip-flop and saw how it works similarly to the SR flip-flop, except that it has this feedback so that if both inputs are 1, then on the rising clock, the output toggles rather than going into a sort of undefined state. In this video, I want to actually build this and take a look at how this works in practice. So here I've built a JK flip-flop following this circuit diagram here.
The only problem will be timing, because if the clock stays high, it is uncontrollable. If the clock stays high. So first of all, we have this little circuit here in the front, this capacitor and this resistor here, that will make sure that no matter how long the clock is, we only get a single pulse. So I'm not quite sure what you are referring to, but you know, I mean, I also have no clue about. Maybe you already know something that I will learn about now.
And I wanted to kind of walk through a couple things. One thing I noticed though when I was building it was in the diagram here I got a couple things, or I got one thing wrong, which is that this is actually the K input and this is the J input, because J corresponds to setting. So when this goes high, we want to see the Q output go high, and then when this input goes high, then the Q output should go low. So K resets. So I just had that labeled wrong, but otherwise everything is fine. So I went ahead and built this. And I'm using the 74LS02 for the NOR gates. So on the top side of the chip, I'm using the 2 NOR gates there. And then this chip over here is the 74LS11, which is a triple 3 input AND gate. So I'm using these 2 AND gates that have 3 inputs each for these AND gates here. If I hook up power here, it should go into some state or other. So it looks like this is the Q output that's on. And then I can also connect my clock over here. And I've got a clock circuit over here. And basically what's going on here is that these two...
I was just checking if I have the same, if I have that chip, but I don't have that one.
Switches are tied to ground through these pull-down resistors. And then when you push the button, it goes high. So both of these are connected via these green wires to the 2 AND gates. So
because we will keep watching a couple of them now.
So those are the K and the J inputs. Also going into the AND gates is our clock. And so the clock comes in here and it's going through this RC circuit. So there's a capacitor here, which is a 0.001 microfarad capacitor, and then a resistor here, which is a 1000 ohm resistor. And then the output of that goes into these 2 white wires, which go into another input on both of those AND gates. And then the outputs of those AND gates are these blue wires that go to the inputs on 2 of the NOR gates over here. The other inputs of those NOR gates come from the outputs, and so those are these 2 yellow wires here. And then also the outputs of these go back around to the AND gates, which are these yellow wires that go back over here to the AND gates. And then also the outputs of these NOR gates go to these 2 LEDs. So this is our Q, and this is our Q complement. So if we push the K input, if we send that high, then that should reset the latch and Q should go off. And indeed it does. And if we push the J, that should set it and Q should go on. And indeed it does. And you see it goes on with the clock. So it's not immediate when I push the button. It happens on the next clock signal because this is gated on this clock rising edge. So now because this is a JK flip-flop, if we put both inputs, J and K, high, we should see this toggle. And it's not toggling. But sometimes it does. And if I hold it at just the right angle or poke at it, oh, there it toggled. Now it's occasionally toggling. Make sure I'm pushing both of these buttons. Yeah, sometimes it toggles. Oh, there it toggled a couple times. And what I'm finding is that this circuit is pretty inconsistent. So what I'm going to do is, rather than trying to push those buttons, if I put a little jumper in here across that button and then another jumper here across this button, that's the same as inputting a 1 for both J and K. So this should be toggling right now, each time the clock rising edge goes. And you see, oh, now it's sometimes toggling. Now it's toggling again. Now it's actually working pretty well. But it's definitely very inconsistent. And it turns out there's a good reason why it's behaving inconsistently. Yep, there it just stopped. And now it started again. There's a very good reason that it's behaving inconsistently. And in order to understand what's going on here, really the only way to really see what's happening is to use an oscilloscope to take a look at the signals in here. So I'm going to start by just looking at the clock input, just so we have a reference of what that looks like. And so here it is. This is our clock. You can see it's going on and off, and it looks like it's about twice per second. Each of these divisions here is 100 milliseconds, so over 10 divisions, it's pulsing twice, so twice per second. And the next thing I want to look at is the output, because this is what we want to see toggling, with each clock pulse. You can see our clock is pulsing here again at twice per second. So each of these pulses we would expect to see our output toggling, and right now it's not toggling. Although, yeah, if I kind of hold my hand at the right place, I don't know, it's kind of flaky, but sometimes it toggles. So I'm going to look at the output here and see what that looks like. And here's our output, and it looks like it is actually doing something. Oh, and there you can see it actually toggled, and now it's high. Okay, so it's kind of inconsistent, and there it toggled again. And so when it is toggling, it's toggling at these clock rising edges, which is what we want. But where it gets interesting is if we zoom in, other way. So if we zoom in and look at that rising edge of the clock, you see there is something going on here. And if we zoom in even more, what you see is pretty interesting, which is when that clock goes high, the output does in fact toggle, but it toggles back and forth a bunch of times before then settling somewhere. And that's actually why this is behaving so inconsistently, is because it is toggling, which is what we want, right when that clock goes high, but it's toggling again shortly thereafter. And if we look at this, you can see the period here is about 84, 82 nanoseconds. So every 82 nanoseconds here, this is toggling on and off. That actually makes some sense if you look back at the circuit diagram here, because what's happening is this pulse is coming in and the output is toggling, but as soon as it toggles, that feedback goes back around to the input, and it toggles again, because this clock pulse, even though we're trying to look at the leading edge of the clock, if this pulse, so the clock of course is, this is on for 250 milliseconds, this is on for quite some time, but this pulse should just be looking at just that very first instant when it turns on. But if this pulse is too wide, then, and the output switches before this pulse goes back to zero, then it will switch again, and it'll switch again, and it'll switch again, and this is a phenomenon called racing. And that's exactly what's happening here, is when this pulse goes high, it's switching on, but then it's immediately switching off and on and off and on. And if I can get this where it's toggling, you see sometimes it does toggle, but it's totally luck of the draw, because it switches on and off and on and off and on and off, and then eventually it gets to here and it settles into whichever state it happens to be in. And so sometimes we get kind of lucky, sometimes, and it toggles, but not always. And the reason for that is this RC circuit. Now I mentioned before that the capacitor I'm using is a 0.001 microfarad capacitor, and the resistor is a 1000 ohm resistor. And so if you multiply those together, you get the time constant of this RC circuit, which is effectively gives you some indication of the width of this pulse. And in this case, this time constant is going to be, I think it's 100 microseconds, but we can actually measure it. So let me look at the clock, or the pulse input here for this.
What kind of probes are those, by the way? I like those, that you can just like stick them into the breadboard. I want those too. I only have these, the ones with like the hook, And then I attached here, you know, like a cable to it so I can plug it into the breadboard. But this is way cooler what he has. I want that too. Does anybody know what those are called or how I could find those? I mean, I have also a Rigel here, so if I find the same kind of probes, it should work, but I don't know. Well, I know that you can buy accessories. It's just like I'm specifically asking which one are those. Most of the... Oh, you can pull the hook off. I totally forgot. You are absolutely right. You're right. They can pull that off. I completely forgot. You just reminded me. Does this work? Oh, that might actually work on the breadboard. That might... It's not keep sticking in, but it should hold. You're absolutely right. I'm a complete idiot. Okay, then never mind. Thank you. Oh, well, I don't know if mine actually work. It's quite a thin, short piece. It felt like it could work, but maybe it's really not long enough. I don't know.
Circuit. And put that here on channel 2. And here you see that pulse. And so if we zoom out, it looks great, right? This is kind of what we're looking for, right? When the clock goes high, this pulse just quickly pulses. The problem is that pulse is not quick enough. And so you can see here, it's 1 microsecond. So 1 microsecond pulse. And for that 1 microsecond, we get this on and off and on and off. And then finally that gets back down to this area here where it's considered a 0. And then it finally settles down. So what can we do about this? Well, there's a couple things we can do. One is we can try to make this pulse shorter. So right now this is 1 microsecond. We saw that if we zoom in here, measuring the period here of this on and off, it's 80 nanoseconds. We can try to get this pulse down. So if we can get it to 100 nanoseconds pretty easily if we go from a 1000 ohm resistor to 100 ohm resistor. So let me try to swap that out. This is the resistor here.
In circuit while it's
And
connected
put the 100 ohm
to
resistor
electricity.
in. And so here you see, okay, we have a much smaller pulse, but it's still not quite working. And we're frankly getting into the limits of what we can do on a breadboard. This kind of high speed, tens of nanoseconds type of stuff. These breadboards really aren't made for that because within
I don't think it's about smoothing the pulse,
straight.
right? It's about just a very fast pulse and very accurate timings, I would assume.
Capacitances and inductance and all sorts of stuff, and that's why just me kind of waving my hands over it where it was changing the behavior of it. In fact, just now you see it went low. So now it looks like it's going high then low and staying low, but I bet if I stick my hand in just the right place I can maybe get this to toggle. Yeah. And I'm not changing anything, I'm just kind of moving my hand around. And it's just because my hand is changing the capacitance because I'm grounded. And you can see there, it's now it's toggling, but now it stopped toggling. So really we're getting into, and you can even see, this rising edge of our clock is not, on this time scale, it's not a real sharp rising edge. And again, that's just because
Feldy. Yeah, I'm. So what Lava Thief is kind of saying, I'm also kind of wondering, is maybe not the better strategy to somehow, I don't know, like delay the output or make that kind of like stick longer, kind of in a similar way how we like debounce a button, right? I don't know. I'm not quite sure if that would work, but the idea would be that once it changes, it sticks for a period of time, and that way your input pulse can be more inaccurate. I don't know. But my assumption is, I guess, you would actually just make that really well timing, you measure this exactly. And when you build the chip, you obviously have a lot more control over the length of the paths, and exactly you basically control the whole thing, which is different. As Ben has said, we get to the limits of a breadboard because there are so many variables that influence these extremely high speeds. And so I guess that's the issue with the breadboard. But in an IC, when you manufacture one, you control everything, so you can be very accurate.
Because the breadboard, there's limits to what we can do.
What is RC network?
We're not detecting a nice clean, or we're not generating a nice clean pulse like we were when we had the larger resistor in there. And again, it all comes down to, we're really pushing the limits of what we can do on a breadboard. And in general, this particular way of detecting the rising edge by using an RC circuit like this is pretty fraught in a JK flip-flop like this because of this racing condition. You have this racing where, if this pulse isn't narrow enough.
Resistor capacitor network. I've heard this term before. I've never. I guess now I understand what that means. That is a resistor capacitor network. Bcamp, is your question why it's racing, or why we chose to make it racing, or what's the question?
And it's it needs to be just a few nanoseconds really. Then the output is going to feed back in, and it's going to toggle more than once per rising edge of the clock. So what can we do about this? Well, in the next video, I'll show you a much better way to build a JK flip-flop that doesn't have this racing problem at all. And that's something called the master-slave JK flip-flop. It's much more robust, and we shouldn't have any problems getting it working on a breadboard. So in the last...
Bcam, can you just spell out your question again? Even with that clarification, I don't understand what you mean. When I connect to the ISC channel, I count as a watcher? Yeah, well, your account is then idling in the channel. That's how the bot... that's the only way how the bot can check who is there, by looking at the people in chat. Thanks for the Twitch Prime sub, Ethan. Well,
in this video, we built a JK flip-flop that didn't work all that well. We used an RC circuit to detect the rising edge of the clock, but because the JK flip-flop toggled so quickly, we encountered this racing phenomenon where it would toggle many times for each clock pulse. And we found it was really difficult to fix, almost impossible to fix on a breadboard, to get that clock pulse to be so short, the pulse that we're generating with the RC circuit from the rising edge of the clock, to get that to be so short that we would only toggle once.
Bcamp, the reason why we want the JK flip-flop is, I believe, for the toggle, and the previous flip-flop didn't have a toggle. This switching between things. But when you implement the toggle, now you get that racing, because now the input is always coming back to the output is always coming back to the input, and that's happening too fast, so the race thing happens. Porky Poop, couldn't you artificially make the race condition unimportant by elongating the wires going through flow? Yeah, that seems like the hacky solution to the problem. Imagine your computer just having like random wires and coils coming out just to make that signal like slower to make your flip-flops work.
We found it was almost impossible to get that working robustly.
By the way, I just about the long wire, the delay thing, that's actually something I learned about a while ago. Delay memory, is it called delay memory? Computer delay line memory. Damn, that blew my mind. Is that it? Yeah, look at that. How insane is this? Check this out. So this is memory, okay? So this is how how something is stored, like how data can be stored in memory, right? Like imagine at a time where kind of like this kind of RAM or so didn't really exist, okay? How do you store something? So here, you use delay lines, and what does it mean? Let's see if there's a good description here. So when bits were entering from the computer, it would twist the end of the wire. This would result in a wave. That wave is then traveling along that metal thing, like the same way how when you like, I don't know, imagine like you are whipping a rope or something. You see the wave in the rope like traveling, right? It travels slowly. You can watch that. So basically, you are when the bits are coming in, you shake the wire, and this wave is traveling through that wire, and that takes a while until it arrives basically at the start again. And then you just repeat that again. You know, like you can have so many waves on that thing that fit on that. Then it's like full, and then you just keep repeating that and always like make the wave travel around, and that's the way how you can store a couple of bits. So apparently 1,000 units were typical on a board with only 1 foot square. And when you wanted to read it, then you just decided, okay, now let's let that wave arrive and read out the bits again. That's so crazy. Yeah, like how did someone ever think of that? Exactly. I saw this in some YouTube video, and it blew my mind. It was a computer file or something. Delay.
So ever since I uploaded a few.
Or it might have been this video. E-block, how do delay lines work? Yeah, I don't know exactly what I watched. But I came across this a while ago, a couple of years ago. And it just... Here, let's check that out really quick. That's just... I don't know. I find this incredible.
Hi there, a few weeks ago on my RC Model Reviews channel, I looked at this core memory. So if this is the sort of thing that interests you, go over to RC Model Reviews. I'll put a link in the description of this video, but I've got some more old tech that
Oh, Numberphile has a video on it. Then that might have been the one I watched. I felt like that's the... astonishing old calculator. Yeah,
1963,
I believe.
if you
Clostall.
wanted to do calculations, you had a mechanical calculator, like this wonderful Odner Brunsviga. But it's all mechanical.
This is from him.
This guy,
I bought that from him.
63, Bob Reagan, worked at Frieden Incorporated, maker of mechanical calculators, had this idea. Let's invent an all-electronic calculator. Indeed, nothing mechanical in it. It's all electronic. And I've been lucky enough to not just get one of them, but to meet and talk with the late Bob Reagan, who came by and helped me repair 2 of them. Signed by Bob Reagan, August 2006. This is a cathode ray tube out of an oscilloscope.
Look at the guys which are restoring the Apollo guidance computer set. Thanks for reminding me of that. I also remember seeing that. There's this group that is coming together for restoring the old computer. A couple of different, I believe, YouTubers are working on different... yeah, I don't know, they assembled like a team to restore it. Like I remember one guy was a person who just built a complete replica, another person who has like done like software emulation about it or so, and they all come together in this like hotel room or something and restore the original one. Yeah, it's an ongoing series. 3 days ago I think I saw the first video where they are announcing this project, I believe. Oh damn, I need to watch this for sure. Oh my gosh, this will kill so many hours. Where's the start? Apollo 4, 3, 2. Restoring the... Yeah, maybe I've seen this because this has a lot of views. This was probably the first video. Yeah, insane. Yeah, thanks for sharing, CMAX. So that channel, if you want to look it up, is Curious Mark. Anyway, let's quickly just switch to the delay line. Here it is.
Over here is a little speaker that goes boink, little magnetic coil that
Boink.
goes boink, and launches a pulse. A little doink goes around here on the spiral of piano wire, steel wire.
Mind
It
blowing.
spirals in, then spirals out, and a couple milliseconds later, it gets to the far end where there's a tiny microphone, a microphone over here, which goes out into an amplifier and then into the circuit boards. So the memory of this calculator is all acoustic. Every time you type a number into it, the bit stream of the number is represented continuously as vibrations in this wire. The alternative, of course, is what we do today. You'd have solid state memory. Well, solid state memory, well, there's let's say there's 6 entries in the stack. Each one has, say, 10 digits. It's more than that, it's 13 digits. Well, let's say 10 times 6 is 60 digits times 4 bits per digit.
Your
It's
long
on the
wire
order
idea
of
is the correct opinion.
250, maybe 5. I would need somewhere between 200 and 500 transistors. And each transistor is costing me $1. That's big bucks. And on top of that, it takes up space. So rather than using transistors as we would today for memory, put all the information in acoustic memory. Okay, I'm working on this. My problem is in August of 2006, I got it working. It was working in November of 2013. Today, I'm sorry guys, it's sort of not working very well. And I'm going in with an oscilloscope. The oscilloscope is there. Okay, so unfortunately you can see it's dancing around. If we type a number in, bam. I can see that 2 of the scanning boards are working. I can also see that I've got some troubles in the arithmetic board and the logic.
Yeah, just incredible, just amazing. It just keeps blowing my mind. I can't get over this fact of storing data in like this wire that is just like going around in a circle. This is just how extremely smart are some people. Like, who would have ever come up with this? This is so ingenious. It's amazing. And by the way, the guy here, Cliff Stoll, who is talking here, is also awesome. He has several number file videos with him. He likes to talk a lot about the Klein bottle. You can also buy that from him, actually. And he will ship that to you with a personalized message and say thank you. He even makes selfies with your bottle before he ships it to you. What an incredible person. There's also recently Brady Haran started the Number File podcast. So along the videos now there's a podcast where he's interviewing various mathematicians, and one of the people that Brady Haran interviewed is Cliff Stoll, and so he talks about Cliff Stoll's life. So if that old guy intrigued you, that was a fun interview. But all of the interviews are really fun. All of the people that he interviews is very interesting, very insightful, very cool. And what makes Cliff Stoll even cooler, especially for us here, in case you didn't know, how do I look for this? I guess I can just search for this. If you have ever heard of the book The Cuckoo's Egg, this story of was it West German hackers infiltrating stuff, and he's from the US and he like tracked that back. All that story, it's in this book The Cuckoo's Egg. There's also a kind of nice like documentary kind of movie, like it's like a documentary at the same time, kind of a movie, a retelling of those things, and he's playing himself in that movie, so it's fun. I watched it as well, and so yeah, so he was the guy in that story. He was the person that kind of like tracked down that hacker. So he also, yeah. What a legend! What a legend! He's incredible. Here, wait, give me a second. 1 second. 1 second. I'll show you something. Yeah. Here, this is the box the Klein bottle was delivered in that I bought from him. Look, he wrote he drew that on it. He even wrote in German. You know, he's from the US. He wrote the German word for fragile. Zerbrechlich. Yeah, even on the other side, like empty glass bottle in German there. That's where it was delivered in. Yeah, some people are just so cool. Yeah, I'm a real fanboy. This guy is just amazing. Klein bottles sale, I guess. I don't know. Here, kleinbottle.com. If you wanna order yourself one, you can order it from his store here. I ordered like a medium one, maybe. Was it a medium or a baby one? I don't remember. Might have been. Yeah, might have been a medium one. I don't remember. Yeah, there's also a video where he's storing those Klein bottles. He's storing all these Klein bottles under his house, and it's kind of like a crawl space. So he built his own kind of like remote controlled robot thingy that can drive and navigate around there, that he is like controlling with a small screen in that office where he was just standing and showing us this machine. So it's like yeah, it's like crazy. You need to live like him. Yeah, what a legend. What an idol. Okay, let's continue.
On a breadboard. So what can we do? Well, there's another way to build a JK flip-flop, and that's this circuit here, which is called a master-slave JK flip-flop. And so what you'll see if you look at this is you see there's essentially two SR latches built into this. There's one here and then one here. And you can think of this as having your set and your reset, and in this case this will be the Q complement and this will be the Q output, and then over here this will be the reset and the set, and then this is our Q output and our complement Q.
Good choice.
So these are these two SR latches.
Good choice,
which you can look at my previous video on those. But then outside of that you have these AND gates that are essentially gating the clock, or gating the SR latch based on the clock. So for the moment, let's ignore these feedbacks. We'll get to that in a minute. But if you look at just these two inputs of the AND gate, the J input and then the clock, or in this case, the K input and the clock, basically what we're saying is, this SR latch is not going to be active unless the clock is high. So when the clock is high, then J will pass through and set, or K will pass through and reset anytime the clock is high. So this is just sort of like an SR latch with an enable, if you want to think of the clock in that way. And then same thing if you look at the slave over here. On the slave side, you've got an SR latch as well. The inputs are coming from the master, but then instead of the clock input coming into these AND gates, you've got the inverted clock input. And so the slave is only going to be active when the clock is low. And so the interesting piece of this is that you're never going to have a situation where both of these SR latches are active at the same time, because the clock is either going to be high, in which case this one's active, or the clock is going to be low, in which case this one is active. And so if you want to set this flip-flop, you want to get the Q output to be high, then you bring J high, and then you toggle the clock high and low. And so with J high, when the clock goes high, then it's going to set the first latch. And so the Q output of that first latch is going to go high. Then when the clock goes low, that enables the second latch, and that Q output gets fed through and sets the second latch, which causes this Q output to go high. So you can see setting the J input, toggling the clock high then low, causes the Q to get set. And then the same way with K, if you set K high and then you toggle the clock high then low, then it resets this latch, and then when the clock goes low, it resets this latch, which resets the output, so it sets Q to 0. So effectively, it's kind of a two-step process where the clock has to go high then low. Now, what about...
This seems to be a better solution than to our long wire porky poop, don't you agree?
This is a JK flip-flop, so we should have that property where if J and K are both high, then the output should toggle each time the clock pulses. So in that case, if J and K are both high, when the clock goes high, the first latch is either going to set or reset depending on what the current output is. So if the current output is that Q is high, then it's going to come around here and this AND gate is going to turn on and it's going to reset. But if the current output is low and then the complement output is high, then this is going to come around and the top AND gate is going to turn on and it's going to set. So essentially this first latch will output on this Q the opposite of whatever's currently being output over here, if both J and K are set and the clock goes high. But it's fine if the clock stays high, because this second latch is not going to be enabled. If the clock is high, then when we invert it, this is going to be low. These AND gates are both going to be off. This latch is not going to be active, and so this output will stay stable. So it doesn't matter if the clock stays high for whatever period of time. This first latch will switch, but the second one won't, until the clock goes low. Once the clock goes low, then that second latch enables, and the output of the first latch gets fed into the second latch. So whether that was setting it or resetting it. And then when that second latch either sets or resets, that's when the final output changes. And of course, at that point, if the output changes, it doesn't matter what's getting fed into the first stage over here, because our clock is low at this point. And so these AND gates are both going to be off, and so nothing is going to change here. So this circuit essentially has the exact same behavior as the first circuit that we were looking at, except that we don't have this issue of trying to make sure this pulse is so narrow that we don't have this racing where the output toggles and then it toggles again and toggles again and toggles again over and over, because we're not trying to use an RC circuit to create a pulse out of our clock. We're using the fact that the clock goes high to set one latch, and then when the clock goes low to set the next latch based on the first latch. And that way our feedback can't get back around to the input until you have a full clock cycle. And so this way this will only toggle once per clock cycle, and we don't have to deal with any of the really stringent timing requirements where we're looking at this 40 millisecond propagation time and so forth. So I've gone ahead and built this circuit, the master-slave JK flip-flop, and just like last time, I've got the two inputs here. This is our J and our K input, and again they're tied low through this pull-down resistor, but then when you push the button it goes high. And so those two inputs go into, this is again our 3-input AND gates. So both of the inputs go into the two AND gates, and then this white wire is connecting our clock, and so we'll connect our clock into that. And then of course
Moro Zilnik. Yeah, that's true. The wire would be too long. That's why we are not talking about a regular copper wire. We are obviously, of course, like who would have questions? We are talking about, a fiber, a glass fiber. Then we have like dotted, what's this called? The things to, oh God, what are they called? The things that you place in long fiberglass things. They are like dotted with some chemical that re-emit the light to basically make it strong again. And so we have that, and we go through the ocean one time, and then we come back.
The third input is the feedback that comes back around, and that's these two green wires here. And then the output of these AND gates are the two blue wires that go up to our first two NOR gates, which are the top two NOR gates on this 74LS02. And then, the outputs of those are connected back to the inputs of these two yellow wires, and the outputs of those come to these first two LEDs. So these two LEDs here give us a way to see what's going on at this point here. So this is our Q complement for the first stage, and this is our Q for the first stage. Then those outputs go over here to another, I guess this is a 74LS08, so just a 2-input AND gates. And also connected to those AND gates is our clock. Except this time the clock is coming, so this is our original clock. It's going over to a 74LS04 inverter, and then coming out of that inverter and going into the AND gates here. And then the outputs of those AND gates go back to our 74LS02, our NOR gates, and here we're using the bottom two NOR gates for these. And so that is, that's these blue wires. The blue wires are, the blue wires are here, coming out of our AND gate, going into our NOR gates, right? So that's those two blue wires. And then, of course, we've got these two yellow wires. These two short yellow wires are the crossovers here between our inputs and outputs of the NOR gates. And then the outputs of the NOR gates are these two yellow wires that go over to our two LEDs. And so this is our final Q output, and this is our Q complement output. So let's hook it up to power and see what happens. So I'm going to hook into the power on our clock that I've got running over here. And so the first thing you see is, of course, looks like Q complement is on our first stage, and then of course Q complement is on our second stage. And if I hook a clock up here, okay, nothing happens. But I should be able to set and reset it. So if I hit J, that should set it. So Q should go high. And in fact it does. Of course you see Q goes high first on our first stage and then our second stage. And then if I reset it, it resets. And the other thing that I'll show you is if I put our clock into manual mode, so here I can just manually activate the clock that way. What you'll see is if I go ahead and try to, let's see if I want to set this. So I turn on the J input, and of course nothing's happening because our clock's not doing anything. When the clock goes high, you see the first stage changes, and then it's when the clock goes low, the second stage changes. And now, I've set the output by inputting a 1 on our J input and toggling the clock high then low. So this is a JK flip-flop. It should toggle. So if I give a 1 on both inputs, and actually I'll just let the clock run, you see with each clock pulse, each time the clock goes high, the first one toggles. Each time the clock goes low, the second one toggles. And so if you just look at this bottom left LED, that's our Q output of our flip-flop, and you see it's just going high, low, high, low. It's toggling, which is exactly what we'd expect. And of course, because we don't have any of the crazy timing requirements here, this is going to work very consistently. We're not going to have any of the flakiness issues that I was having with the JK flip-flop that was using this RC circuit to try to detect the rising edge of the clock.
He also said RC circuit.
And in fact, because it's much more reliable, this master-slave arrangement for building a JK flip-flop is typically the way that JK flip-flops are built in practice. So now that you understand how the JK flip-flop works, in future videos, rather than building JK flip-flop from all these components, we can go ahead and use a prepackaged JK flip-flop, in this case the 74LS76, which is a dual master-slave JK flip-flop. So it's got two, that's what makes it a dual, there's two of them. And of course master-slave JK flip-flop, you know what that means, that's what we just talked about. And so if you look at the flip-flop here, you see it's got of course the J input and the K, here it is, the K input. I don't know why it goes all the way around there, but so you've got your J input, your K input, your Q output, your complementary Q output, so that's what it means, complementary output, has both a Q and the inverted Q outputs. And this one also has a preset and a clear. And so the preset and clear are these two other inputs that basically just force it to either set or reset. So rather than, it kind of bypasses the clocking mechanism, and so you can just force it to reset or reset. So it's just kind of another little feature that these have. And then the other thing you'll notice is the clock input here says it's inverted. It has this little bubble here. And that's actually absolutely correct, because this is a master-slave JK flip-flop. And you remember that the final output, the Q output, doesn't actually change until the clock, both goes high and then goes low. And so, unlike this first JK flip-flop that we tried to build that triggers on the rising edge of the clock, the master-slave JK flip-flop, because it requires the clock to go high and then low again, the output triggers on the falling edge of the clock. And so that's indicated in the symbol for it with this little bubble here, showing that this is this clock input is looking at the falling edge, is what that bubble means. So in the next video, I think we'll hook a couple of these 74LS76s together and build a binary counter.
Cool.
So
okay, so it's 6 p.m. Zoding is going live soon. That means I don't want to stream for a lot longer. I think the question also was coming up earlier if I have a longer stream today. No. Oh my god. What is happening? So the question also came up if I stream longer, but nope, not today, because we got a host Zoding. So he's going live now, which means let's build this. This seems to be a short video. It's only 5 minutes long. So let's see how long this video goes with the binary counter, if we already start building our program counter or not. But yeah, so maximum streaming for another hour or so. I'm not smoking.
In the last video, we looked at the JK flip-flop and ended up building one, but found it was a little bit challenging to build on a breadboard because of the importance of the timing around the edge detection. So in this video, I want to look at the 74LS76, which is a chip that has a JK flip-flop built on it, and try to build something kind of practical or interesting with it. And there's other chips that have JK flip-flops, the 74LS73, I think, and I think pretty much anything you find that claims to be a JK flip-flop, if you've got the data sheet, you should probably be able to figure out how to set it up. But in this case, I've got the 74LS76, and you can see it's got two JK flip-flops in it. If we just look at one of them, you've got the output. So there's the Q output, and then the Q inverted output. And then, of course, you have the J input and the K input somewhere. Here it is, K input. So you've got the J and K input, and then the two outputs, the Q and the inverted Q. We've also got the clock input here, which, of course, we want. And you can see it's an inverted clock, which means that this is going to switch states on the falling edge of the clock. Which doesn't make a big difference, but it does mean, just we should expect to see the state change on the falling edge. And they show the whole clock signal here, because I think what they're implying is that, after a complete clock signal, then it changes state. And this also has a preset and a clear input. And so preset and clear are basically a way to ignore the clock and just set the output. So they're active low. You can see the little bubble here is telling us they're active low. So normally they'd be high, preset and clear. But if you take preset low, then that forces the Q output high, regardless of what's going on with the clock or the J and K inputs. So it's just kind of an override to preset the output. And then clear is the same thing. If you take that low, then it forces the output low again, regardless of what the clock or J or K inputs are doing. And then, if both preset and clear are low, then both the outputs go high, and that's kind of an invalid state. And in fact, they have a little note for us here. It says, note, this configuration is non-stable. That is, it will not persist when the preset and or clear inputs return to their inactive high level. So basically they're telling us, don't do that. But this is just kind of an override kind of thing. So we'll set both of those high so that they're not being used. And so I've set this circuit up using this chip, and you can kind of, let me see if I can fit it all in here. But you can see, of course, we've got VCC and ground to provide power to our chip, so those are hooked up there. And then the preset and clear are both high, which is they're inactive. And then you can also see I've got the J and the K inputs are set high. So basically I'm inputting a high and high to the J and K, which means that when our clock pulse comes, we'll toggle. And you can see the two outputs. So if I connect the clock up to our clock, which is pin 6 here, you can see it's toggling with each clock pulse. And so if we look at it together with the clock, you can see it's toggling each time the clock is pulsing. Now, an interesting side effect here is it's kind of easier to see if I take out the inverted Q output, but an interesting side effect here is that you can see the output is toggling at half the speed of the clock. And so this circuit is sometimes referred to as a divide by 2, because whatever speed the clock is coming in, the output here is that speed divided by 2. And that can get kind of interesting if we keep dividing by 2. So if we take the output of the first flip-flop and we use that as the clock for another flip-flop, we see that now this second flip-flop is toggling at half the speed of the first, which is toggling at half the speed of our clock. And of course we can keep going. So now if we hook up 2 more of these, we can take the output of this one and feed it into the clock of the next one. And then we can take the output of the next one and feed it into the clock of the last one. And if I increase the speed of the clock a little bit, you'll see something interesting that's happening here.
It's counting.
As we're dividing by 2 each time, what we've got is a binary counter. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. It's counting in binary. Whenever we're running a program...
Okay, cool. Yeah, so why do I not order from AliExpress? Mostly because of shipping times. I don't know if like the parts that I would order there are necessarily worse. I mean, all those parts are manufactured in like, I don't know, obviously mass production plants somewhere. But yeah, mostly it's just the time. The few cents that you are saying, like if I pay 10 cents or if I pay 15 cents for one of these chips, really doesn't matter in the end to me. At least at this point, you know, I don't. That is not really the driving cost here. My work time I put into is way more expensive than those parts. So it's much easier to just order from, you know, a store that has everything. On AliExpress, you also have to source them from different stores. I guess maybe there are big stores where they have everything, but it's kind of hassle everything. So I ordered from another store. Also we want the breadboards, we need the cables, we need all the other stuff, the LEDs. Yes, you can source everything from AliExpress, or you can source everything from DigiKey or other cheaper kind of stores, but yeah, in the end it doesn't really matter that much. The whole 8-bit computer from China costs $80 or less. I ordered parts too. Nice. Yeah, I'm sure you can make it work. I was mostly worried, for example, also with the quality of the breadboards. I personally don't know because I've bought the expensive ones. Somebody in another YouTube video mentioned that he had problems with cheaper breadboards, that some connections weren't as great, and that was frustrating apparently. So yeah. Like, we are talking here prices that I know for many people, like especially when I was younger, I can relate to when I was younger and basically didn't have a job, that yes, prices would matter. I would spend ages to find the cheapest thing and save a little bit. I obviously understand, but you also have to understand that I have a job, I earn money, right? So this is spending money on a hobby kind of thing. So I don't mind a couple of euros more. I waste more money with other things. I'm sure for streaming this with all the lights on that are here on and all the the electricity that I'm wasting because of the setup, I'm sure this will cost me more than what I've paid more for this, for these parts, basically. Yeah, I don't know. Yeah. Yeah, but mostly it's shipping time, and it's easier to just order from a store that just has everything and it ships fast and those kind of things. However, I did order a couple of things from AliExpress the other day. It just takes now a month for them to arrive, but I'm really looking forward to them. I ordered foot pedals because I want to build foot pedals so I don't have to click by hand, so I can do the scene transitions with my foot. And that would be kind of fun to build on stream as well, because obviously there's no like immediate solution how to make that work. So we will likely like learn about. I imagine right now that I will use there's like a WebSocket API plugin for OBS that we use that plus like a Raspberry Pi maybe, or just an Arduino or so to interface with the foot pedals that then send these commands basically to OBS. That's kind of the idea. But yeah, future us problems after this or in between. I don't know yet. Is the stream going to be a long-term thing? The problem is I cannot keep up the daily schedule. That's insane. It's killing me right now. I definitely need to take it down. The problem is that I like it too much right now. So right now I don't want to divert from the daily thing, but I can't sustain this long term. Impossible. I'm going crazy already. It's more than $100, so I don't think it's a couple of cents. Yeah, it's a couple of cents per component, and there are quite a lot of components, I guess. But yeah, it's like Ben Eater's original price is $250, and I spent more on that because I was also experimenting with different kinds of LEDs, what looked better. I wanted to get the more expensive breadboards. Yeah, and it sucks. I know. I live in Germany. I live a very privileged life. Our the money we earn at jobs is in the top compared to the whole world, most other countries. $100 is not much for me, which I hate it. Okay, I don't like it. It makes me feel really bad every time I think about this, that I'm living this extremely privileged life, that I don't care about $100, just because I was lucky to be born in Germany and have a good paying job. And it fucking sucks to read people that are watching. Like the other day we had somebody from India who was telling me that a hairdresser's earning like €2 a day or so. It fucking sucks. It's unfair. Don't know what to tell you. It just sucks. You are the person who asked about the wire on Reddit. I went to the Baumarkt and bought some Klingeldraht. Gonna try it out tomorrow when I'm back home. Oh yeah, I also heard that Klingeldraht is the thing, but did you find like a good thickness that seems to work? And did you find different colors? Because it's the other problem I had. I did find Klingeldraht, but often it was just like one color available also, which I would have also liked to have different colors. But Klingeldraht is also what I heard is basically what you would be looking for. It's even worse when you're born in a country where you are either rich or poor and there's no middle ground. Yeah. I have a colleague who is also from Hong Kong. I think about it this way, that's $100 more into the third world economy. You mean if you buy it, from like these kind of stores? I know. I mean, that kind of trickle down economics is pretty bullshit, but whatever. let's tell us that so that we feel better. You found some wires on eBay? Yeah, it seems like a good thickness. Like I said, can try it out tomorrow. There's white, red, and yellow. That's at least a little bit of color variation. Why should I change it to science and technology? Are we not chatting a lot? Basically, we have YouTube reaction content and we are chatting a lot. We don't do anything science and technology, basically. Wouldn't you agree? Okay. So this video, okay. Program counter design. This seems to be like a really kind of important video that gives us, I think for the first time, at least looking at that image, a better overview of how this kind of computer kind of works, I guess. So, yeah. Oh, Hex, is it a good idea to make a dual studium study at HP as Informatica? FYI, I applied to HP and IBM. Those are the two places that I applied for my dual study as well. So I also did a dual study in. Are you also from Baden-Württemberg, around that area? Are you going to study in Stuttgart basically, or Böbling? I think the dual study system is great. I think the dual study system depends heavily on the company you are with. And from my experience is that the people at HP were also pretty cool. I didn't go to HP in the end because my dad worked for HP and I didn't want people to think like I only got the job because of my dad, so I went to IBM. But my roommate was at HP. We had many HP friends. We interacted a lot with the people from HP. And it seems that HP is also generally one of the better companies to do it. If you have so I think it's definitely a good solution. If it's something for you, in the end you have to decide if a dual study is what you want to do, or if you have the choice between different kind of companies, what you want to do. But if you think this is something you would be happy with, I would say it's a good choice. For shorter distance, I will use different wire for breadboards with different colors. What kind of wire would you use? That I'm confused. That switching languages confuse you? Yeah, mostly because I only speak English, so speaking German requires quite some thinking. I also make at the Teig wait, what? You should be able to post links. I don't know why not. I think so. I mean, it might auto mod you, but then I will take care of it. Do you know some people who studied KIT? Yeah, I also know people who studied KIT. KIT also seems to be a good place. KIT was also one of the universities I thought about when I was thinking about my bachelor's, but in the end I went with the dual study program. I have a set like that as well. Over here. The problem is that these are rigid. The lens, the connections that you are making are so unique and different constantly. If you do care about making every wire the perfect length that it looks nice, then this will probably not work. If you not really care and it's okay if it's like a bit too long and you bend it outwards a bit and it has a little bit of curvy stuff, if you don't really care, then I guess it's fine. But if you would want to make it like really, really nice, then you definitely have to cut every single wire because the lengths are so different. I would recommend against pre-cut. Yeah, I also feel like it will never be the exact length. You will always have to choose like basically the longer one and then kind of bend it out of shape just to make it kind of fit, I would assume. Yeah, and the colors we are choosing in this build here is based on the functionality. So we kind of, just with one glance, we know, for example, a yellow wire is a control wire for us. And like the yellow wires here are control wires, and we know the white one is the clock signal. I mean, yeah, I tried to wake it and later rewire it. We are at video 28 right now of 44. Uh, 0.6 millimeter breadboard jumpers. Let's see. I think wasn't it? I don't know. So the thickness that we are using is AWG 22 American wire gauge, and now I don't know what your 1/0.6. It sounds like the inner one is 0.6 while the outer one is 1. Now if you compare, like, the inner one is here 0.3. So that's this double as thick. That seems kind of a bit extreme, to be honest. Oh, it says on it 22 AWG? Okay, then I don't know what. I guess it's millimeter, not millimeter squared, because this is like I don't know the translated word right now. Okay, so the 0.6 millimeter is the außen, like that one here. All right. Okay, yeah, that sounds good. But that is from the price not really different from. So I ordered from here. Hook. So the price here. So these ones here are 15 euros. This is the one that's what I bought. What's the difference between those two things here? I don't know. I don't know. Might be the same thing. Those are the ones I bought. Those are exactly this. This is basically what Ben Eder also uses, and it's 15 euros. $22 AWG is perfect. All of these wires are 22, and this is also what Ben Eder is using in his build. That seems to be. I would feel like that's the perfect thickness. That has been, yeah, I don't know. That seems super, like, perfect, I feel like. What's the length? The length is, does it say on here? Wait, it says on here. It's 25 feet per spool. I think that's like 7 meters or so. 25 feet, 2 meters. Yeah, 7.6 meters. It's definitely not enough for the blue and the green one. So we have a lot of blue and green, and both of them are basically empty. I have a little bit of green left, but the blue one is empty. So I bought like 2 of these packs. In class, you used 18 AWG. How much is that? I have no relation and feeling for that. Oh, wow, it's quite a bit more. Let me think. So wait, let me look at this again. Okay. No, so to me this, look here, wait, we have macro shots. Ah, crap, the camera's empty. Let me show you in the macro shot, like how tight that is. I feel like 22 is really perfect. I couldn't imagine it. That seems quite of an extreme bigger that you are using, or that you used there. Find that kind of curious, to be honest. Here, breadboard. Almost try to show this. Okay, so here, I hope that's big enough for you to see. Like, see, that's 22. Like, that fills like that hole like really nicely. There's not really much play. See? Like, I feel like this is pretty good. Are all breadboards the same? I have no clue. I mean, the spacing between them is kind of a standard. But yeah, it could be that some of those holes are larger. I mean, I could imagine that the 18 also fits. Because they're still, it's still quite large. But that feels like that would be like the maximum. That almost feels like it would probably go like really strong in there and would like be like really crazy connection. I don't know. Yeah. Anyway. What Druckschalter? Do you mean the latching one that like switch toggles between different things? Or do you mean the regular push buttons? And that's actually also something we played around with. So a couple of streams ago, I got another order from Mauser because I wanted to exactly find a nice buttons. So I bought like a couple. I bought a couple of different ones to find a good one. So we got this one here. I'm an idiot. Yeah, so we got this one here, but like I said, it took us. I ordered a lot of them, a lot of different versions. I went to Mauser and spent like quite a few hours looking for them, and then I ordered all of them, and then we checked them out on stream. Which one is a good one? Looks like a cherry switch. Yeah. Here I also replaced my other buttons, like the regular push button. So for example, for the clock here, I also replaced it with one of these, so they kind of look the same now. I would have to look up the exact name of this one because I ordered like a lot of different ones. Yeah, I couldn't find these stuff like this at Conrad or Reichelt or so. So my go-to store so far that I've been extremely happy was Mauser. Mauser Electronics has been really surprising for two reasons. First of all, they have everything. It is a massive store. It takes ages to find stuff, especially when you are just like looking for something like these buttons there. But they have then all the different kinds. Yeah, you're right. I need to here add my ad label. They have all the different kinds, and they ship from the US, which worried me for two things. First of all, shipping time, and second of all, I was worried about the import duty. But it's all already included. So they they pay all the duties so that you have absolutely no issues getting that. I had a 500 euro order from there. No problems at all. The price already includes all of that when you order. And shipping is extremely fast. It takes like 3 or 4 days maximum. It flies basically immediately over. It takes like a day or so to fly to France, and then from France it like gets to your distribution center, and then it gets to you, and that each of those steps take about a day. That was like absolutely incredible. I'm a fan of Mauser now. Yeah, and there I got the cables. I found the correct breadboards. I found like these weird blue LEDs that I'm using now. I found these latching buttons. Yeah. Occurred to me that if you want pedals, you might want to look at Flight Sim Community. That sounds like a good idea. However, I would assume that the stuff that the Flight Sim community uses are proper pedals that like cost money. The same thing with, I was looking at music gear, because you know, guitar players and generally musicians use also foot pedals. So I thought about buying like a MIDI foot pedal thing, but they are all expensive, because these are kind of like good products that you know, you only have buy like one or two or so. The Logitech Series foot pedal, let me see what that costs, because anything over €5 is too much. Or maybe everything over €10. €10 would already hurt. Are you talking about something like this? That I would never. That's not what I'm looking for. Anyway, what I ended up figuring out is tattoo foot pedals. This is exactly what I wanted. So I didn't know. So I'm not a tattoo person. I have no clue. I stumbled over this by accident. But tattoos, obviously, they need a foot pedal to control when they activate the needle. And so there you find the cheapest kinds of foot pedals that you can want. Spending a lot of breadboards is fine. €10 too much. Well, it's too much for just a simple switch. I just want a switch I can push with my foot, right? It's a cheap ass plastic thing with just a toggle thing. I don't need more. I don't need any of the kind of music like features that come with it. The gaming stuff, USB controllers. I don't know what kind of drivers. I don't care about that. All I want is just a switch that is large enough for my foot to press, basically. And I could have made my own one. I also thought about that. With these breadboards, there come these metal sheets. Let me show you. Each of these breadboards have these metal sheets for whatever reasons in the package. And then so I thought you could build your own like cheap ass pedal with, you just angle them a little bit, and you know, and then you isolate them, and then when you like do that, now there you have your foot pedal, basically. That's also my other alternative. But then I found out about these tattoo pedals, and these are just cheap ass pedals. They cost like nothing. They cost like €2 or so when you order them from China each. And so I'm able to buy like 10 or so of them, or 8 of them, and so then I can put them all under my desk to control stuff, you know. I mean, so let me rephrase. If there were, for example, an Elgato Stream foot pedal thing that integrates with Stream Deck already with all their software features, and you get like a nice array of like 5 or 10 foot pedals that you can put under your desk, and it looks fine, and you can buy it and everything works, and it costs €200, I would have bought that. But because I have to do everything myself, I have to build the software, I have to rate everything myself, I have to build the foot pedal thingy, and integrate that all with OBS. Because I have to do all this work, I want to buy cheap pedals. Does that make sense? Yeah, I saw some foot pedal controllers on Amazon like this. Yeah, of course I looked there as well. But the problem is I still would need to write software for all of these, because they are not... I mean, there are some MIDI controller plugins and stuff for OBS, but that all looks janky. And then I figured... And then they also sometimes... I'm not sure the one you linked right now, how much that has. But I only found like one with like... Yeah, so the one you sent me there, but it's not available to buy right now. But there's an alternative. It's like €30. But it's only 3. I have even more scenes than that, right? I have 1, 2, 3, 4 4 cameras, basically 4 sources of camera input with my laptop. I have, you know, different, and there's more stuff that I want to control with it as well than that. And so like 3 pedals is already not enough. If you build a fully integrated foot pedal software you use, you would pay me 200 euros? Probably. Anyway, we talk too much crap. Let's continue. I wasted time.
Program on our computer, the program is stored in RAM as a list of
I mean, if it's like a hacky solution, I can do that myself, right? Like, I wouldn't mind buy a full-featured product that integrates with Stream Deck and whatever. You get the point.
instructions. And in order to execute each instruction, we have to fetch
Binary with 3 pedals. That's kind of funny. It's kind of hard to do with 2 feet, though. You kind of need to have like weird. Yeah, I know it's holding his life. That's why we need to hurry so we can host him.
it from RAM. So for example, in the 8-bit computer, whenever we're running a program on our computer, the program is stored in RAM as a list of instructions. And in order to execute each instruction, we have to fetch it from RAM. So for example, in the 8-bit computer that we're building, a program will normally start at address 0, and we'll fetch that and execute whatever instruction is in address 0. Then we'll go to address 1 and fetch that and execute that, and then address 2, address 3, 4, 5, and so on. And so we've got to have a way to keep track of which address we're on, and the way that we do that is with the program counter. So in this video, I'm going to talk about what the program counter is, how it works, and we'll go ahead and build it. So of course, as the name implies, the program counter needs to be able to count. And of course, we've seen in previous video that we can build a binary counter using JK flip-flops. So a counter like this that counts.
As far as I know, you have 3 cameras. No, I just counted. I have 1 camera right here, 1. Overhead, 2. Canon, 3. The laptop screen is another input. It's not a camera, but it's kind of a camera, it's another input, 4. And then you just reminded me I also have a thermal camera, so we have 5. So those are just the different sources. But then there's more I want to control. So maybe I want to, for example, control the add overlay that you can like see up there in the corner. Maybe I want to add that. Maybe there's more stuff I want to do with the stream that I want to be able to control at a later point in time. Not right now, because those things. I have a USB microscope here as well, which is also hooked up, but we are not really using for this stream right now. But that's another option that we might want to have hooked up. I'm running into issues with my Stream Deck already. So the Stream Deck has 2, 4, 5, 15 buttons. And it's completely full with buttons. There's no other space I could put stuff on. And I wish that now there's a bigger Stream Deck, but it just came out after I bought this one, so I don't know.
Counts in binary is definitely going to be an important part of our program counter. And in fact, our program counter is going to be a 4-bit counter, similar to this, because...
Yeah, but an iPad doesn't have buttons. It's a touch screen. This I can basically, press blindly. I know roughly where the stuff is. I can feel the buttons. Yes, why do I use this? I could also just move my mouse and click the stuff in OBS. Why do I use this? Why do I want foot pedals? So I have my hands free to do that. You understand? Like, yeah, you get it. You get it.
The memory that we built has a 4-bit address. But in many ways, the program counter also works a lot like a register, like the A register or B register. It stores a value. Unlike the A register, general purpose register, like the A register, the value that the program counter stores always has a specific meaning. It's the address of the next instruction we're executing. But like any other register, it needs to be able to put that value out on the bus. We might want to be able to read a value from the bus and instead of just counting in order, be able to jump to a different address arbitrarily by putting some other value into the program counter. And so the program counter has a few control signals going into it. So one is...
sorry for interrupting, but you were writing, you could use your tongue. Do you know, what's his name? Taran? Is his name Taran? From Linus Tech Tips? Linus Tech Tip. Taran brain interface. So Taron van Hemert is the editor, or is one of the editors from Linus Tech Tips, and he is like crazily optimizing his editing all the time.
You may have noticed.
And he has also experimented with like, you know, brain to computer interface to see if maybe he can use that to as shortcuts for controlling, but it hasn't quite worked out. But he sees kind of the future hopefully to be there. It's the guy with the macros, yeah. It's the guy who has like 5 screen decks or so around his keyboard.
Is this program counter out. And that works just like the A register out or the B register out. It tells the program counter, put your whatever value you're storing onto the bus. And when I say storing, you know, the counter like this, you see, well, it's counting it. But if we stop the counting by disconnecting the clock, you see it's storing a value. It's storing, in this case, the value 3. You know, 0011 is 3 in binary. So, you know, the program counter is going to store a value. And of course, we want to be able to put that value out on the bus using this program counter out. And so whenever we enable that signal, the contents of that program counter will be asserted out onto the bus, and then some other part of the computer, for example, the memory address register, can then latch in whatever that address or whatever that value is into that memory address register. We also want the program counter to be able to read values from the bus, because we don't just want to count. We don't always want to execute instructions 0, 1, 2, 3, 4, 5 in order. In some cases, we might want to jump around. If we want to have a loop in our program, for example, maybe we want to execute instruction 0, 1, 2, 3, and then when we get to instruction 4, we want to go back to instruction 0 and just run a loop like that. So we need to have some way of not just counting, but being able to put some other value into the program counter. And so to do that, it works very similarly to any other register where we have some sort of in control signal that says take whatever's on the bus and latch it into the value that you're storing. So in this case, that's the jump signal. And so whenever we enable this jump signal, it says take whatever's on the bus, or at least 4 bits worth of it, the 4 least significant bits of the bus, because this is a 4-bit counter, not an 8-bit register like these other things. Take those 4 bits and put it into the program counter. And then that'll be the next address that we execute. So this jump signal works a lot like the A register in signal or the B register in signal, instruction register in signal, RAM in, anything like that is taking the value from the bus and putting it into this register, if you will. And so the program counter does work a lot like a register, but of course it's also a counter. So it does need to be able to count, just like this. And of course we don't want it to count on every clock cycle. So right, this is clock, every time there's a clock pulse, this is counting. And we don't want the program counter to count every clock pulse. We just want it to count or essentially increment once per instruction cycle. And an instruction might take multiple clocks to execute. And so this last signal here, this count enable input signal, allows us to enable the program counter to count. So whenever this is active, the program counter will actually increment on each clock cycle. And so we can activate this input when we want to advance to the next instruction, let the program counter count up by 1, and then disable it so that it doesn't continue to increment while we're executing that instruction. And then when we're ready to execute the next instruction, we can go ahead and increment it again. So our program counter is going to be based on this simple binary counting circuit using 4 JK flip-flops. But we're also going to need some additional logic to handle our output and our jump, our ability to load in a value from the bus and this enable option. So to make things a little bit simpler, I'm going to use the 74LS161, which is a 4-bit binary counter, synchronous 4-bit binary counter. Synchronous just means it counts using a clock. And if we look at what's inside the 74LS161, we've got these 4 JK flip-flops, very similarly to what we have in the binary counter that we built before. But we've also got a bunch of other logic, which turns out to be quite useful for what we're trying to do. So one thing that's kind of nice is that the clock that comes in is positive edge triggered. Because remember, a master-slave JK flip-flop, the clock is inverted here because the output changes after the clock goes high and then goes low. So the output changes on the falling edge of the clock. So there's an inverter here that means that with the 74LS161, the output changes on the rising edge of the clock, which is a little bit nicer for us because we want everything in our computer to happen on the rising edge of the clock. The other nice thing that this gives us is a lot of this logic helps us load a value into here. So rather than just counting 0, 1, 2, 3, 4, and so on, we have the ability to load a specific value in using this data A, data B, data C, and data D inputs. So if we put some value on A, B, C, and D, some 4-bit value, and then we enable this load signal, then that value will show up out here on the output. And then subsequently, when the counter counts, it will count from that value. And so that helps us implement this jump function, where we want to be able to load a new address in from the bus to jump to an address, out of order for loops and that sort of thing. And the other thing the 74LS161 gives us is it gives us an enable input. And these enable inputs essentially enable whether the counter is counting or not. And so these basically implement for us this count enable function. So this allows us to, when this is not active, the program counter just holds on to whatever value is in it. But then when we activate this enable, then with each clock pulse, it counts. And so that's built in for us very nicely in the 74LS161 using these enable signals. And so just to go over the functionality of the 74LS161, it's pretty straightforward. It's got the 4 outputs that we want, and it's got 4 inputs that we can use to load an arbitrary value into those outputs using the load signal. It's got these enable signals that allow us to enable whether it's counting or not. And then, of course, the clock, which each clock pulse, if the enables are active, then it counts. And then the other thing it has is a clear, which just resets it to 0, which will be kind of handy, but not critical. And then this ripple carry output would be, this is a 4-bit counter. If we wanted an 8-bit counter or more bits, we can cascade these by taking this ripple carry out and feeding it into the clock of the next one. So this chip, the 74LS161, gives us almost everything that we need for a program counter. It gives us the ability to control whether it's counting or not with that enable. It gives us the ability to load a value in, to implement this jump functionality by using this load pin. But it doesn't give us this program counter out, because that we need some tri-state logic to interface to the bus here so that we can control whether the value that's coming from the outputs of this chip is actually going out on the bus. And for that, we can use the same chip we've been using for all of our other registers, the 74LS245. And so that, again, has these tri-state buffers that allow us to enable or isolate those bits. And of course, this is an 8-bit thing. We're only going to use 4 of them, but that's fine. This is the same chip we've been using in our A register, B register, RAM, used it in the instruction register. We've used this a number of times. So we'll use this again for our program counter.
All right. You found a better one, a cheaper one on Amazon? Yeah. So the problem is that's also a USB one. If you think about connecting 8 USB devices to a computer, I would also then, get a USB hub just for that. And then also we don't know if that is like configurable, because it's like a HID USB keyboard. It says like, is it then all the same like key that it's outputting? Is it configurable? So I don't know yet. Anyway, but like I said, I found like very cheap like tattoo foot pedals on AliExpress that fulfill exactly what I need. It's just a button, and then we can write some code for like Arduino or for Raspberry Pi also to use them. That I think that would also be fun stream, I guess. Yeah. Right. But one small thing I can show you. So if you go to Amazon and you look for these tattoo foot pedals, this is really risky to search right now, I feel like. There's this one kind of foot pedals that I saw these search results look very different than when I search. Okay, so for example, these here, for €4, or for 350, these foot pedals are exactly what you can buy from AliExpress, and these ones here as well, like these ones here for also €5 with shipping. You can buy them directly from AliExpress, and you can get them for like €2 or so. So this is like double the price. Funnily, these are also kind of odd, like weird people that are selling these, like these companies here that are selling these, sell all this kind of random crap. And they also say that it might be delivered, next month, in a month. So this is just drop shipping. Like they don't have that stuff in Germany right now. You order it and they will ship it. They just buy it straight from AliExpress, and you just pay the markup for them to put it on Amazon. You can just buy it yourself from AliExpress. So this is just a typical drop shipping store thing. Anyway, cool. Okay, so it's 6:50. We watched the program counter video, and now we head into the program counter build. I guess we keep that for next stream. I think I will slowly wind down. It was definitely a shorter stream today, but like I said, the main task for today is not to make any progress, but our main task for today is to be able to host Zoding. That's why I started earlier. I kind of procrastinated. I should have started earlier, then we would have had a longer stream. Yeah. But then you don't have to worry about customs. You also don't have to worry about customs when you order from AliExpress. First of all, because it's super clear. Well, let's say you might still have to worry about customs from Amazon, because do you think those drop shippers deal with customs? No, they just also make it ship from China to your address, and then they intercept it at the customs. However, second thing is, under €20 you are duty free anyway, and above €20 up to 150 or so you just need to pay the VAT, and above that you need the other stuff. So if you just buy for below €20 a couple of these foot pedals, then it's all good. Is your Point Adventure Docker file supposed to work? I'm trying to set it up. Can you specify what they changed, who changed what? Because nobody changed anything, I feel like. Nobody should have changed anything. That should be the nice thing about Docker, that it just should work. However, yeah, I don't know. I know what would they have changed. Who would have changed what? But also the problem is Point Adventure is slowly getting pretty old. I get more and more people that have issues. Like I receive more and more messages like yours that people have issues, but usually with running the client, because the run times, the graphics libraries or so, they just don't work anymore on modern Ubuntu. So you have to like use like an old Ubuntu 14 or so to run it. At least what I have ordered from dropshippers, they will reship it from inside the EU. Yeah, might also reship it, who knows. They now require the client maps in order to set up the server. This has always been the case, that you need the client thing. Maybe it wasn't like fully initialized or so what you did, I don't know. Yeah, like if we look at GitHub liveoverflow, Point Adventure 3. If you look in the, I don't even remember. Is it in the setup? Post game server. It's not in the Docker image. Yeah, do you know how you run Docker? It's in the Docker file also. Somewhere it is. In some setup script. Somewhere tools. No, wait. Docker compose in here maybe? Let me see. Master server. Wait, I find it. Give me a second. In here. I mean, there's one dependency that might have changed actually. That's true. I can check really quick. There's somewhere a wget. Somewhere is a download of a file. Am I blind? Here in the README. Okay. I guess you'd have to do this by hand. Did you do this? Did you get that file? Or is that not available anymore also? Do you mind sending me a link to a structure you're using? I'm trying to find the right one. They're just, yeah, that's, the problem is also I bought like a dozen different ones. So figuring out which one this was exactly will be a little bit difficult. But I can try. Wait, let me see. Give me 1 second. I might. No, I don't have it in the package right now anymore. So what I was saying is this wget, that download there, are these client files. So what the client would download, what you would also need for the server. I asked the creators of Pwn Adventure if they can just host those files so that the server setup is easier, that you can just download those files. And so this is what is supposed to be in that folder. I mean, what could be that they removed it or that something else changed or so. So I don't know. Super Soaker, if you don't behave, I won't send you that link. Let me see. Let me try to find that, and then we cut the stream. So how? Crap! 1 second. How are you wearing headphones? I've only watched half the stream with headphones and my ears are sweaty. Let me introduce you to the amazing products of open back headphones. They are open here. Their air goes inside of here. They are not closed. This was a revolution to me as well. I only learned about this like 2 months ago or so. Yeah. This has been a revelation, and since then I love open back headphones. I can recommend. So these ones are really expensive. These ones are a bit more affordable. Those are the Sennheiser. Doesn't it say on here? Oh, HD 599. I like those also. I might even like them a little bit more than these in terms of how comfortable it is to wear, but yeah. I mean, yeah. I mean, they are. I mean, can you kind of see that? Let me show you. So see how I can like. Oh, okay. Wait, that's a bit. Wait here. I put this here. See like how this like shines through. It's like not really like fully open. There's still like a fabric and stuff. But the idea is that it also doesn't isolate you from the room. So when you put them on, I mean, this can be like a problem for you. You still hear everything around you. It doesn't isolate you. Like it basically dampens no sound around you. You can hear everything. So if you get headphones because you want to drown out other noise or you want to isolate yourself, then it's not a good choice. But for example, I want to still hear the doorbell. I want to hear my dog coming in. And also it feels so weird when you like have like typing sound, for example, and that sound is dampened from regular headphones. Then that's kind of, I don't know, it feels annoying. Like I hear everything, like every small noise I hear. So it feels very natural, but you still have headphones on and you can like listen to whatever you want to listen to, and you don't have to use speakers. So yeah, those are the pros and cons. And yes, I also have noise cancelling headphones. I don't need them at home because there's no noise I need to cancel out. But for example, I hate public transit without noise cancelling headphones. I need them to drown out the city. Only use them to drown out fan sound. Yeah, that's the issue. You will still have that fan sound. That's then a problem. Anyway, let me still find that those buttons. I want to make a proper parts list with also the flathead LEDs that I've been using, but I still don't know because there's still a lot of modification happening for this. So I want to make sure I get the proper parts list in the end. So DPDT. Oh gosh, so which one is it here? Okay, maybe I shouldn't do this on stream. There's like so many that I ordered. Okay, let's quickly check. I can easily identify it. Let's go quickly to Mauser and search for 629 GPBS. That's not the one necessarily we want. I'm just going for one. So this must be on this series, but so on this image you can see all the different ones. So now we gotta go in the data sheet. That's how I basically looked for them. And now then here are different ones. So it could have been one of this, either this one here or this one here. Let's see, those are the latching ones. This is blue and this is brown. It should be this one here then. I believe it must be this one here. Latching, yeah. So it should be this one here. So yeah. GPBS 850L. Yeah, these are the 660S. Okay, cool. I guess that was it. We found the buttons. Yeah. Okay. Sorry, everybody. It was kind of a shorter stream. We basically didn't accomplish anything. We just watched YouTube videos. But we did learn about the delay circuit memory using acoustic waves. I think that was pretty cool. Yeah. Tomorrow will be probably another stream. Maybe tomorrow it will be maybe a bit longer. I still don't know when I stream tomorrow. It might actually be earlier in the day. So there are two options that I haven't decided yet. Either it will be earlier in the day, basically around 1 p.m. German time, because then we can like watch together the next episode of my my weekly video that I'm releasing every Sunday. So we could watch that together, or it will be then later in the day towards the afternoon, evening. Anyway, so let's rate Soding. Oh, and movie recommendation. True. We had a movie recommendation. I actually might put that back on the background and rewatch it again. That kind of sounds fun. Twitch.tv. Okay, alright. Thanks so much for hanging out with me. And Toding is also a very chill stream, so maybe hang out and check out his stream for a little bit. See you there.